Welcome to the video lecture on infinite series. Let's start by considering the sequence with the nth term 1 over 2 to the n minus 1. So if n is 1, this becomes 1 over 2 to the 0, which is just 1. If n is 2, then we get 2 minus 1, which is 1, so we get 1 half. If n is 3, then we get a fourth. If n is 4, we get an eighth, and so on. Notice that these denominators are getting bigger and bigger and bigger. So 1 over something big gets small. Therefore, the limit of our nth term is going to go to 0, which means this sequence converges. Now, what we're going to do that's new in this video lecture is we're going to add the terms of our sequence together. So we're going to start by taking just the first term by itself, so that would just be 1. And then we're going to create a new sequence of these what we call partial sums. So first we've just added the first term to itself, or just the first term by itself. Now we're going to add the first two terms together. So 1 plus a half is equal to 3 halves. Then we're going to add the first three terms together. So 1 plus a half plus a fourth turns out to be 7 fourths. And then we're going to add the first four terms together, so 1 plus a half plus a fourth plus an eighth, which turns out to be 15 eighths. And then we're going to add the first five terms together, so 1 plus a half plus a fourth plus an eighth plus a 16th, and that gives us 31 sixteenths and so forth. So you continue this process, creating a new sequence of what we call partial sums. So obviously 1 is equal to 1, 3 halves is the same as 1.5, 7 fourths is the same as 1.75, 15 eighths is 1.875, 31 sixteenths is 1.9375, and we could keep on going. What does it look like this sequence is converging to? It looks like these numbers are getting closer and closer to 2. So what we're going to do is we're going to model this situation by thinking about a piece of string that's 2 feet long. And we're initially going to cut it in half so that we have two pieces, 1 foot long each. So the first piece we're going to set aside, and we're just going to, I'm going to label that 1 foot long, and I'm going to call that A sub 1 here. And then A sub 2 is going to be the other piece that was cut. We're going to take that piece and we're going to cut it in half. So when we take a 1 foot piece of string and we cut it in half, we're left with a half of a foot. So we keep half and we save half. Now from the other half that we're putting aside, we're going to take that half and cut it in half again. So that's going to be our A sub 3, and that's going to be 1/4 of a foot in length. Then we're going to take the other half of that 1/4 that we're not saving over here, and we're going to cut it in half again. So that would be A sub 4, which is going to now be 1/8 of a foot, and so on. So we continue this process. Now if we take all these pieces of string that we have over here and we start stacking them up and adding them together, we're going to start with our full 1 foot piece of string, and then we're going to add in our half of a foot, and then we're going to add on to that our 1/4 of a foot, and then to that we're going to add on our 1/8 of a foot, and so on. If we continue this, how long is this going to be? What is this converging to? Well, it obviously can't get any longer than that initial 2 feet that we started with. And so this is going to have as its full length, if we continue this process, we're going to get back to the original 2 feet. So these partial sums that we're talking about seem to converge to 2, modeled by this situation that we're talking about with these lengths of string where we add them back together to get to that 2. So this is called a sequence of partial sums, and we're going to call them S sub 1, S sub 2, S sub 3, S sub 4, and so forth. So that S sub 1 is going to equal the 1 that we got up here, just from the very first term by itself. S sub 2 is going to be the 1 plus the 1/2, the first two terms added together, and that was our 3 halves. S sub 3 is going to be 1 plus a half plus a fourth, which was that 7/4 that we got. S sub 4, 1 plus a half plus a fourth plus an eighth, which was that 15/8. And then S sub 5 is going to be 1 plus a half plus a fourth plus an eighth plus a 16th, which is 31/16. So this sequence of partial sums then just becomes this new sequence: 1, 3/2, 7/4, 15/8, 31/16, and so on. Now, can we come up with a formula for this new sequence here just by looking at it? Well, what we can call it is we're going to call it S sub n, the nth partial sum, and it's going to be sort of this generic formula for this nth term right here that would generalize each of these terms if we let n be 1, 2, 3, and so on. So looking at those denominators, you see that we've got those powers of 2 in the bottom. This is n equals to 1, this is n is 2, n is 3, and so forth. So we don't want just 2 raised to the n, because we want actually 1 less than that power of 2. For example, the first term here is 2 to the 0. The second term is actually 2 to the first. The third term is 2 to the second. So in that denominator, we actually want 2 to the n minus 1, and that will generate all of those powers of 2 on top, or on the bottom. Now on top, what we want to notice here is that these numerators are close to powers of 2, but they're off by 1, because 4, which is 2 squared, minus 1 would give you 3. So this number right here is actually 2 squared minus 1. This number right here is close to 8, which is 2 cubed minus 1. This number right here is close to 16, which is 2 to the 4th, but minus 1. And 2 to the 5th is 32, minus 1 makes it 31. So these numerators are going to be 2 to the n minus 1, like that. Okay, so that's kind of how we can come up with a formula for these partial sums. And what we're going to notice then is that if we were to take the limit of these partial sums as n goes to infinity, which would be the limit as n goes to infinity of this formula that we just derived, what would that limit be? Well, initially, 2 to the infinity is infinity, and 2 to the infinity on the bottom is also going to be infinity. So this is acting like infinity over infinity. But we have L'Hopital's rule at our disposal, so we can apply L'Hopital's rule here and take the derivative of the top. Derivative of 2 to the n is 2 to the n times ln of 2. And on the bottom, the derivative of 2 to the n minus 1 would be 2 to the n minus 1 back again times ln of 2 as well. Now notice that 2 to the n minus 1, what is that the same as? Well, if we break up that exponent in the bottom, 2 to the n minus 1 is a 2 to the n times a 2 to the negative 1, since if the bases match, you add the powers. So that means these 2 to the n's can cancel, these ln of 2's can cancel, and 1 over 2 to the negative 1 is the same as 2 to the positive 1, or just 2. So we just proved that the limit of these partial sums was equal to 2. And so in fact our guess back up here that this seemed to be converging to 2 is correct. So we just showed that the limit of partial sums is equal to 2. Now what we just created here is called an infinite series. Formally, the notation that we're going to see is this sigma symbol, which is the Greek capital letter for S, and it stands for sum. Typically you have an index. It can be any letter at all, but usually for infinite series it's an n, and it can start at any number that you want. Most often it would start at 0 or 1, but it could start at 2 or 3 or 4 or whatever you want. And if we want an infinite series, then that means we're going to go up to infinity. And what we're doing is we're adding together all of those terms in our sequence. So that's what this a sub n represents, the generic term. So if we let n be 1, that would be a sub 1. If we let n be 2, that would be a sub 2. If n is 3, that's a sub 3, and so forth. And what this sum does here, this sigma notation, is it adds together all of those terms in your sequence, and this would continue on forever. So this is called an infinite series. Now, by definition, we're going to say that this infinite series will converge if the sequence of partial sums converges. So we're going to have to find S sub 1, S sub 2, S sub 3, S sub 4, and figure out maybe a generic formula for S sub n and see if that S sub n partial sum converges. And if it does, then that means this sum converges. If it doesn't converge, then it will diverge. So if the sequence of partial sums diverges, then this infinite series diverges as well. So initially, the only way to tell if an infinite series is going to converge is by looking at the partial sums. We'll add to that eventually, but for now, that's the only way we know how to tell whether or not an infinite series converges or diverges. So let's consider this infinite series right here. This would be your generic a sub n term right here. And what we can show is that if we let n be 1, we would get our a sub 1. If we let n be 2, we'd get our a sub 2. If we let n be 3, we'd get our a sub 3. Now if we start adding up a sub 1, and then a sub 1 plus a sub 2, and a sub 2 plus a sub 3, and so forth, we're going to get some partial sums. And that's what these represent right here. So S sub 1 is actually just the very first term. S sub 2 is the first term plus the second term, and you end up with 4/7. S sub 3 is the first 3 terms added up, and you get 6/10, and so forth. Now it's nice that they're telling us these partial sums so that we don't have to compute them, but what they want us to do is find a formula for the generic partial sum S sub n, and then use that to figure out if this series converges, and if so, what does it converge to. So if we look at our partial sums here, to figure out a formula for S sub n in general, we're going to need to see what the pattern is here. So if you look at those numerators of our partial sums, 2, 4, 6, 8, 10, those are obviously just 2 times whatever term it is. So 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6. So in general, it looks like the numerator is just going to be 2 times whatever n is. Now the bottom is a little more complicated, but what you want to notice is that it's actually what we call an arithmetic sequence. We're going from 4 up to 7, and then from 7 to 10, and then 10 to 13, 13 to 16. That's adding 3 each time. So we start at 4, and to get to the second term here, the second partial sum, we add 1 3 to it. To get to the third partial sum, we actually have to add 2 3s to our 4. To get to the fourth partial sum, we have to add 3 3s to our 4. So if we start with 4 and we add n minus 1 3s, that's going to get us to that next denominator that we're looking for. And you can verify that if n is 1, then we're adding no 3s, so we just stick with 4. If n is 2, then 2 minus 1 is 1, so we're just adding 1 3, which will give me that 7. If n is 3, 3 minus 1 is 2, 3 times 2 is 6, so we're adding 2 3s and getting 10. So that does work. If you simplify it a little bit, you're going to get this 3n right here minus 3 plus the 4 that we already had, and 4 minus 3 is 1, so this is going to be 3n plus 1. So this would be our generic formula for the nth partial sum. So now what we're going to do with this is we're going to use it to help us figure out what this series turns into. What is the sum of this infinite series? The sum of the infinite series is going to equal to, by definition, the limit of these partial sums. So if we take the limit as n goes to infinity of this generic nth partial sum, that's going to tell us what our sum is. If this converges, whatever that converges to will be our sum. If this diverges, then this infinite series would diverge. So if we plug in infinity, we're going to get infinity over infinity, which doesn't give us anything. That's an indeterminate form. But if we apply L'Hopital's rule, the derivative of the top just becomes 2, the derivative of the bottom just becomes 3, and the limit of 2/3 is just 2/3. So that means that this infinite series converges because we got an actual finite value, and it means that its actual sum is 2/3. So if you were to add up a1 plus a2 plus a3 plus a4 all the way up to the infinite term, you're going to get a sum of 2/3. All right, let's take a look at the next example here. Find a formula for S sub n and find the sum of the series given that the series is the sum from 1 to infinity of -1 to the n minus 1. Now what I find helpful is to write out what some of these terms are. So if we look at the sum from 1 to infinity of -1 to the n minus 1, if n is 1, what are you going to get? Well, this exponent will be 0, and anything to the 0 is 1. If n is 2, 2 minus 1 is 1, -1 to the first is going to be a -1. If n is 3, we're back to an even power, so we're back to a positive. If n is 4, we're back to an odd power, so we're back to a negative, and so forth. So these are going to alternate between positive and -1. And what this summation notation is telling us to do is to add these together. Now these individual terms here are not your partial sums. They're the actual terms in the sequence. So this is a sub 1, a sub 2, a sub 3, a sub 4, and so on. So what would S sub 1, S sub 2, S sub 3, S sub 4 be? Well, that's when you're actually adding these together. So S sub 1 is just the very first term, and that's it. S sub 2 is the first two terms added together. So 1 plus a -1 would be 0. S sub 3 would be the first three terms added together. Well, these two are 0 plus 1 more is back to 1 again. S sub 4 would be the first four terms added together. That's going to be a 0 plus a 0. So these different partial sums are alternating between 1 and 0, 1 and 0. Now, based just on that fact and the fact that this is going to continue, do you think that these partial sums are going to converge? No, this is going to have to diverge because the partial sums alternate or oscillate between 1 and 0. Okay, so these can't converge. So that means this sum does not converge. So this is going to be a divergent sum. Now, can we come up with a formula for S sub n? Yes, we have to be a little bit clever here. We want our sum to alternate between 1 and 0. So what we can notice is that if we start with 1 and we subtract an alternating -1 to the n here, what's that going to give me if n is 1? If n is 1, we want our first partial sum to be 1. So we want this answer to be a 1. So if n is 1, this is going to stay negative, and we'd get a 1 minus a -1, which is actually a 2. So how do I take that and turn it into a 1? I can divide by 2. So that will give me the first partial sum. Let's see if it works for S sub 2. So if n is 2, now this is going to be positive, and 1 minus 1 will be 0. So that works. If n is 3, we're back to an odd, so we're going to stay with that negative, but the negative will cancel out with the minus. So 1 plus 1 is 2. 2 divided by 2 is 1. And if n is 4, we're back to an even, so this turns positive, we're back to a 0. So this does work. It's just a little bit tricky to see where it comes from. Now, what if we were given a formula for this nth partial sum already, and we wanted to kind of go backwards to figure out what the formula for the individual terms in the sequence a sub n were. So for example, suppose that we were told that s sub n was 2n over 3n plus 1. And if you were to plug in different values, you would see that s sub 1 is 2/4, s sub 2 is 4/7, s sub 3 is 6/10, s sub 4 is 8/13, and so on. Okay, we've already done this example earlier. So how would you use that information to go backwards to figure out what a sub 1 is, a sub 2, a sub 3, and so on? So if we can do that, let's also see if we can come up with a formula for a sub n in general. So what you want to recall about these partial sums is that s sub 1, which we know is 2/4 here, is actually just that very first term. S sub 1 is a sub 1. So now we know a sub 1. Okay, so a sub 1 must be 2/4, which is the same as a half. Let's see if we can find a sub 2. So a sub 2 is going to come from the fact that s sub 2, which we know is 4/7, is really the first two terms added up. So a sub 1 plus a sub 2. And we already know what a sub 1 is. So if we were to plug in 2/4, then a sub 2 would be 4/7 minus this 2/4, which turns out to be 1/14. So a sub 2 is 1/14. So how do we find a sub 3? Well, let's look at the third partial sum, which we know is 6/10, and the third partial sum is the first two terms, the first three terms added together. Well, we know what the first two terms added together already is. It's 4/7. So if we replace this with 4/7, then that's going to tell me that a sub 3 must be 6/10 minus this 4/7, which is 1/35. Let's try one more here. So s sub 4, which we know is 8/13, is a1 plus a2 plus a3 plus a4. But we already know the third partial sum, which is the first three terms. These three terms we know add up to 6/10. So if we replace them with a 6/10, then that means a sub 4 would be that 8/13 minus the 6/10, which is 1/65. So that's kind of how you gradually build up to those individual sequence terms. So how about in general? Well, we know that the n minus 1th partial sum would be a1 plus a2 plus a3 all the way up to the n minus 1th term. So the nth partial sum would be a1 plus a2 plus a3 all the way up to a sub n minus 1 plus a sub n. And all of this is all of this. So if I replace this with s sub n minus 1, then what that tells me is that a sub n must be this s sub n, the nth partial sum, minus the n minus 1th partial sum. So this is our relationship to figure out any specific term. Now we know what s sub n is. We have a formula for it right here. So from that we can also figure out what n minus 1th partial sum should be. So a sub n equaling s sub n minus s sub n minus 1 would have to be s sub n, which we know is 2n over 3n plus 1, minus the n minus 1th partial sum would be this same formula, but instead of using n's, we would use n minus 1's. So that's going to look like 2 parentheses n minus 1 over 3 parentheses n minus 1 plus 1. So that's what a sub n will be. Let's clean this up a little bit. Let's go ahead and get a common denominator, and before I do that, let's clean this denominator up. When I distribute, I'm going to get a 3n minus 3 plus a 1, and a minus 3 plus a 1 is going to be a minus 2. So my two denominators are 3n plus 1 and 3n minus 2. This fraction already has the 3n plus 1, it's missing the 3n minus 2. So the numerator would be 2n times that missing 3n minus 2. The second fraction already has the 3n minus 2, it's missing the 3n plus 1. So this would be 2n minus 2, if I go ahead and distribute that 2 across, times the missing 3n plus 1. So let's go ahead and clean that up. Distributing across the top, we're going to get 6n squared minus 4n. And then over here, we're going to get a 6n squared as well, but it'll be minus. We're going to get a 2n, but it'll be minus. We're going to get a negative 6n, but that will be minus minus, so that becomes plus 6n. And a negative 2 with a minus out front becomes a plus 2. So what cancels here? The 6n squareds, a minus 4n and a minus 2n is a minus 6n, and that's going to cancel with our 6n. So this turns out to be 2 over 3n plus 1 times 3n minus 2, and that's what our generic nth term of our sequence must look like. Okay? All right. Now what we're going to talk about next is a very specific type of infinite series called a geometric series. And a geometric series is created by adding together the terms of a geometric sequence. So what's a geometric sequence? A geometric sequence is a sequence that starts with an initial term a, and to get the next term you multiply by the same common ratio r each time. So the first term would be a, the second term would be a times r. Then if you multiply that by r again, you'd get ar squared, and then ar cubed, ar to the fourth, and so on. So in general, your nth term looks like ar to the n. Now if that's your sequence, now to make it a series, you would add up each of those terms. So the first term a plus the second term ar plus the third term ar squared, and so forth. So this is called a geometric series. It's very common. And what we're going to look at is what the sum of a geometric series turns out to be. So there's different cases that we need to consider. The first case we're going to consider is what happens if your r, what we call the common ratio, is 1. Well, think about what this would become. If we have the sum from 0 to infinity and our r is just 1, then this becomes a times 1 to the n. And 1 to the n is just 1, and 1 times a is a. So this is just the sum of a from 0 to infinity, which if you were to expand that out, each term is just a, and we're adding that all up. So if you take a plus a plus a plus a plus a, that's not going to converge because you're adding the same number an infinite number of times. So this is actually going to be an infinite sum, which means it diverges. So a geometric series will diverge if your common ratio r is 1. What if your common ratio is negative 1? Then your series is going to be the sum from 0 to infinity of a times negative 1 to the n. So if n is 0, this is positive a. If n is 1, then this becomes negative a. If n is 2, we're back to a positive a. If n is 3, back to a negative a, and so forth. Is that sum going to converge? No, because s sub 1, the first partial sum would be a, but the second partial sum would be 0. The third partial sum would be back to a. The fourth partial sum would be 0. So this is like that earlier example we had where this oscillates back and forth between a and 0, a and 0, a and 0. So this is going to diverge because it oscillates between a and 0. So now what are we going to get for this sum if r is not 1 or minus 1? So what we're going to do to figure that out is we're going to look at the nth partial sum, so that s sub n. Now one little tricky thing here is to note that the way we've defined our geometric series is that it's actually starting with an n of 0. So you have your first n equal to 0 as this a, then n equals 1 would be here, n equals 2 would be here, and so forth. So the nth partial sum would be the sum of the first n terms. So this is actually your first term here. The nth term is actually going to be when we use a power of n minus 1. So our nth partial sum is just the sum of these very first n terms. So that would be the a plus the ar plus the ar squared and so forth up to ar to the n minus 1. Now what I'm going to do next here is just a little bit of algebra. What would happen if I took this entire statement right here and I multiplied everything through by r on both sides? So the left side would be an r times that s sub n, and if I multiply this right side by r and distribute it across, then this would just become an ar plus an ar squared plus an ar cubed and so forth. And this last one, when I increase that power by one more r, this would become ar to the n. Now what I'm going to do, again just a little bit of algebra, is I'm going to subtract this entire bottom equation from the top one. So all of these are going to become minuses. And what you'll notice when I add down is on the left side we'll get just s sub n minus r s sub n. But on the right side, because of these minuses, these two terms cancel, these two terms cancel, the cubes would cancel, this one will cancel with the one right before it, but what we're going to be left with is the very first term a and this very last term which has a minus in front of it. Now let's factor out this s sub n. I'm trying to solve for s sub n and come up with a formula for it, because if you have a formula for your nth partial sum, then you can take the limit of it to figure out what your infinite series is actually going to do, whether it's going to converge or diverge, and if it does converge, what it converges to. What I can also do on this right hand side, let me go ahead and pull out an a as well. So let's factor out this a also. So what I'm going to do last here to finish solving for my s sub n is I'm going to divide by that 1 minus r. So s sub n will be a over 1 minus r times this 1 minus r to the n. So that's what the generic nth partial sum would look like, assuming that r is not 1 or negative 1. And what we can say then is that the limit of this nth partial sum will be what my sum is equal to. So if this converges, then my sum converges. If this diverges, then my sum diverges. Now the convergence and divergence of this depends on r. So let's look at the two different cases. If r in absolute value is between 0 and 1, which basically just implies that r is a fraction, either a positive or a negative fraction, so that in absolute value it's between 0 and 1. So that's what that means. If r is a fraction, what you want to remember is a property or theorem that we talked about in our sequences video lecture, and that's the fact that the limit as n goes to infinity of r to the n, so a fraction raised to an n, like 1/2 to the n, 1/3 to the n, negative 1/4 to the n, that goes to 0 in the limit. As that power gets bigger and bigger, the denominator of that fraction gets bigger and bigger, so the fraction as a whole gets smaller and smaller. So we're going to use this fact to tell me that this limit then, if I look at this limit of our nth partial sum, if r is a fraction, then this part of it is going to go to 0. So we'll get 1 minus 0, which is 1, times a over 1 minus r. And a and r are both constants here. So this is just going to equal a over 1 minus r. So that means we got a value. So that means this is a convergent series if your r is a fraction. And the actual sum of the geometric series will be this formula, a over 1 minus r. Now what happens if you have an r which in absolute value is bigger than 1, like 2 or 3 or 4? Then what we've mentioned in the past is that if you have an r that's bigger than 1 and you raise it to this n, where n is going to infinity, so if you have something like 2 to the n, 3 to the n, 4 to the n, what's that going to do as n gets really, really big? Well, that's going to blow up and go to infinity. So what that tells me then is that this limit of our nth partial sum is going to have this blowing up to infinity. And 1 minus infinity is negative infinity. Negative infinity times a constant is still negative infinity. So this is going to blow up and go to negative infinity and therefore diverge. Okay? It could be plus or minus infinity depending on these constants out front. But the fact that it blows up tells us that this diverges. So our conclusion here is that a geometric series like this converges only if your r, your common ratio, is a fraction between 0 and 1, and the sum that it converges to is your very first term a over 1 minus r. That's what you want to have memorized as a result of this discussion we just had here. If you have a common ratio r, which is not a fraction, then this will diverge. Okay? So let's put that into practice here with some examples. Determine whether each of the following series converges or diverges, and if the series converges, find its sum. So you should be able to look at this and just know right away whether or not this converges or diverges, because it has the form of a geometric series. If you need to, you could expand this out a little bit. When n is 0, 2 to the 0 is 1. When n is 1, 2 to the first is 2. When n is 2, 2 to the second is going to be 4. And then 2 to the third would be 8, and so on. And we're adding these together. So this is geometric because each time I'm multiplying by 2. Now that 2 is what we call our common ratio. And what we just said is that if your common ratio is not a fraction, then this is going to diverge. And you can see that this sum here would have to diverge because we're just adding on bigger and bigger numbers to it. So this is going to go to infinity. So there's no way that it will converge. So then if I look at this next example here, what is my common ratio? If you need to expand it out, you certainly can, but as you get more practice, you'll be able to recognize that when you have a constant raised to the n, that's a geometric series, and that constant that's inside there is your common ratio. When n is 0, this is 1. When n is 1, this is a half. When n is 2, this is a fourth. When n is 3, this is an eighth, and so on. So each time we're multiplying each term by 1/2. So my common ratio r is a half. And the fact that that's less than 1 means that this will converge. Now, since I know it converges, I can find out what its sum is. And that's pretty rare. Usually for these infinite series, we can't actually compute the sum. We can say that it converges, but we may not know what it converges to. The nice thing about geometric series is there's this formula, a over 1 minus r, which actually tells us what the sum happens to be. So a, remember, is your very first term, in this case when n was 0, which is just 1. And then r is this 1/2. So if we simplify this, we're going to get 1 over 1 minus a half is half, and 1 over a half becomes 2. So the sum is actually 2 if I were to add all these up. The next one here, 4/3 to the n. Now this sum is actually starting at 2. So 4/3 squared is going to be 16/9, and then the next term would be 4 cubed over 3 cubed, so that's 64 over 27, and then 4 to the 4th over 3 to the 4th, 4 to the 5th over 3 to the 5th, etc. So each time we're multiplying by another 4/3. So my common ratio is 4/3. That is actually 1 1/3, so that means it's bigger than 1. So that tells me immediately that this sum must diverge because my ratio is too big. All right, this next one here. Don't be confused by that 2. That's just affecting that very first term. So if n is 1, this would be 2 times negative a half, which is equal to negative 1. If n is 2, when we square this, it becomes a 1/4. 2 times a fourth is going to be a half. If n is 3, that's odd, so this will stay negative. We get negative 1/8 times 2 is negative 1/4. So this is going to continue, and what you'll notice here is that we're multiplying each time here by this negative 1/2 to get to the next term. So your r is negative 1/2, which is a fraction between 0 and 1 when you take its absolute value. So this is going to converge, which means we can find its sum. The sum of a geometric series is always a over 1 minus r. This time our a is negative 1, and our r was this negative 1/2. Be careful with your signs here. So you'll get negative 1 over 1 plus a half, which is 3/2. When you flip that over, it becomes negative 2/3. So this sum is negative 2/3. The next example here, does this look geometric? Yes, because each time what I'm doing, what am I multiplying by? Think of it that way. What do I multiply to go from this term to this term? Well, I multiplied by a negative 4 in the denominator, so in other words, I multiplied by a negative 1/4. My common ratio here is a negative 1/4. 3 times negative 1/4 is negative 3/4. 3 over negative 4 times negative 1/4 is 3 over negative 4 squared. So our r here is a fraction, which means this will converge. So the sum will be a over 1 minus r. The very first term was this 3, and my r was that negative 1/4. This becomes plus in the bottom. 1 plus a fourth is 5/4. So when I flip that over, it becomes a 4/5 times 3, which is 12/5. So there's my sum. The next example, 1 plus e over 3 plus e squared over 3 squared plus dot dot dot. What am I multiplying by each time to get the next term? If you just look at 2 consecutive terms, you should be able to see what it is. If you can't see it, then just divide the 2 terms by each other. The third term divided by the second term, or the second term divided by the first term, and that'll tell you what your common ratio r is. Here you can just see that we've multiplied the top by an e and the bottom by a 3. To go from here to here, same thing. I multiplied 1 by e over 3 each time. Okay, so that means my r is e over 3. And e is about 2.718, so that's less than 3, which means this fraction is less than 1. So this converges, and its sum will be a over 1 minus r. The very first term is this 1, and our r was this e over 3. If I get a actually, let's go ahead and multiply through by a common denominator, which is 3 here. So I'm going to clean up this fraction. 1 times 3 on top will be 3, and on the bottom 1 times 3 will be 3, minus e over 3 times 3. The 3's cancel, just giving me e. So that's a nice way of cleaning up that complex fraction. And then you can just leave your answer like that. For this example here, this looks kind of messy, so you can write out a few of the terms if you like and go from there. What I'm going to show you how to do is just to manipulate these powers a little bit. You have your choice here. If you'd prefer to plug in n equals 0, then n equals 1, then n equals 2, and based on that figure out whether it's geometric or not and what r would be, that's fine. What I'm going to do is I'm going to break up this power here and make it a negative 5 to the n and a negative 5 to the negative 1. And then this 4 to the negative n, I'm going to flip down to the bottom and write it as 4 to the n in the denominator. Then this negative 5 to the negative 1 is like taking a negative 5 and flipping it down to the bottom, which would make it a negative 1/5. Okay, actually let me squeeze in my summation symbol here first. So this would be a negative 1/5 from this piece, and these two both have a power of n on there, so let's regroup it and write it as negative 5/4 to the n. And that makes it a little more obvious that this is your r. So our common ratio is negative 5/4. Is that bigger than 1? Yes, because 5 is bigger than 4. So that means this is going to diverge. Number 11, find all x such that this sum will converge. So what you want to recognize here, and the only way we're going to be able to do this, is to recognize that this is a geometric series, because we are multiplying by the same common ratio each time. What am I multiplying by each time to get the next term? I look at usually these two right here, or you could go between these two here to see what it is. We're multiplying the top by another x minus 1 each time. So in the numerator, our r is going to have an x minus 1, and in the bottom we're multiplying by another 3 as well. And if you verify that, this first term 3 times x minus 1 over 3, the 3's cancel, which is why you just get an x minus 1 by itself for that second term. And then if I multiply that by an x minus 1 over 3, you get this. If I multiply this by x minus 1 over 3, I get x minus 1 cubed over 3 squared, and so on. So it does work. We do have the right r. Now what we need to know that is, if it is geometric, which we just identified that it is, then that series, that geometric series, will only converge if your r in absolute value is bigger than 0 and less than 1. So if our r is x minus 1 over 3, then we need that in absolute value to be less than 0 and then at the same time be greater than 0 and at the same time be less than 1. So let's split this up into our two different options. If I look at the left side of this inequality, we need this x minus 1 over 3 to be greater than 0 in absolute value. Well, you know that absolute values are always positive except in the one case when it could equal to 0. So this is always true except if what we have inside here, this x minus 1 over 3, equals to 0. Then this inequality wouldn't be true. So when does x minus 1 over 3 equal to 0? Well, that's going to happen when x is equal to 1, which would make that numerator 0. So we don't want x to be 1, otherwise this won't be true. If we look at the other side of the inequality here, then we need this x minus 1 over 3 to be less than 1. And that's one of those triple inequalities, if you remember from intermediate algebra, with absolute values. If we want this stuff in absolute value to be less than 1, then that means that x minus 1 over 3 must be between negative 1 and positive 1. So if I solve this triple inequality, I'm going to multiply everything through by 3. So this will become negative 3 less than x minus 1 less than 3. And then I'm going to add 1 all the way across. So we'll get negative 2 is less than x is less than 4. So our solutions for x would be all of these x's between negative 2 and 4, except that 1 is inside of there. So we need our x to be between negative 2 and 1, not including the 1, and then from 1 up to 4. That way we're going all the way from negative 2 to 4, but we're leaving a little hole at 1. So by choosing x to be those values, this series will converge. Okay? Now a couple of theorems here for properties of infinite series. These should be fairly common sense. If we know that the sum of a sub n converges to a, and the sum of b sub n converges to b, and c is a real number, then the following series will converge to the indicated sums. So this says that if you have a constant multiplier, basically a c times a sub n, then that sum is going to converge to c times whatever the sum of just a sub n would be. And that should hopefully make sense, because basically each term is looking like c times a sub 1, c times a sub 2, c times a sub 3, and so on. So if you already know that a sub 1 plus a sub 2 plus a sub 3 converges to A, this C is just multiplying all of them throughout, so that answer should just be your big A times C. And then this second property says that if you have the sum or difference of two or more sequences that you're summing up, then you can just take the sum of the first one, which converges to A, and add or subtract that to the sum of the second one, which we know converges to B. The next theorem says that the limit of an nth term of a convergent series, this kind of gives us a relationship here. If you know that a series converges, then the sequence of terms a sub n has to converge to 0. Not the sequence of partial sums, the sequence of the original terms inside of here. So what this theorem is saying is that if your sum of a sub n converges, if that series is to converge, then the limit of these nth terms, a sub n, has to go to 0. Now the converse of that is a really important theorem called the nth term test for divergence. And it basically says the opposite of this. What it says is if the limit of these nth terms does not go to 0, then the sum of all of these terms in your sequence, a sub n, must diverge. So this gives us kind of a theorem to determine divergence right from the start. So if you take the limit of your nth term inside of that series, so if you take the limit as n goes to infinity of this expression right inside of that sum, if that does not go to 0, then you know that the entire sum itself must diverge. And again, this is called the nth term test for divergence. So, for example, if you have the following series right here, the sum from 1 to infinity of 2n over 3n plus 4. This is your nth term. This determines each of the terms of your sequence, and then we're adding those sequence terms together to get our sum. So what the nth term test says is if you look at the limit of this a sub n, what is this limit going to be? Well, the dominant term on top is 2n, the dominant term on the bottom is 3n, so in the limit that's going to go to 2/3. And that is not a 0. We need it to be 0 if this is going to have a chance of converging. So the fact that it's not a 0 means right away that this series, this sum, must diverge by this nth term test. Okay, but you want to be careful with this nth term test. It's a little bit misleading and confusing. For example, if you look at this next one right here, this is the sum from 1 to infinity of 1 over n squared. So our nth term of our sequence is 1 over n squared. If we look at the limit of that, as n goes to infinity, n gets really, really big, and that's in the denominator. So 1 over something really, really big is going to go to 0. So this does go to 0. So does that mean that this must automatically converge? No, it's not that powerful. All we can say is that if it's not a 0, then it has to diverge. If it is a 0, it could still diverge, but it could also converge. We don't have enough information. So if your limit equals to 0, then you can't conclude that it diverges or converges. You're going to have to try some other test to figure that out or not. And right now we don't have a lot at our disposal. So at this point we probably would have to just leave it open-ended. If we look at this next example here, we have e to the n over n squared as our nth term. So if we take the limit of that nth term as n goes to infinity, this is a nice quick test to use to just kind of visually check right away, because if you know that it fails it, then you're done. If it doesn't fail it, then you can pull out some other tests. So on this one, initially as n goes to infinity, we get e to the infinity, which is infinity, over infinity squared, which is infinity. So we can't really decide anything yet here, but we can use L'Hopital's rule. So if we apply L'Hopital's rule, the derivative of e to the n is e to the n. The derivative of n squared is 2n, and that's still going to give me infinity over infinity. So try L'Hopital's rule again. Derivative of e to the n is e to the n, and now the derivative of 2n goes down to 2. That's what I'm looking for. I'm looking for that power on that n to slowly decrease until it becomes constant. Now the top will be infinity, but the bottom will be a 2, and infinity divided by infinity is still infinite. And the fact that this is not 0 is what tells us that this series must diverge because it fails that nth term test. So here's a summary of the conclusions and the tests that we have so far. To test for convergence, the first thing you can try is if you have or you can come up with a formula for that nth partial sum, which is usually pretty rare. Usually we don't know what that nth partial sum formula is, but occasionally you're told what it is or you have enough information to figure it out. Then, if you take the limit of that nth partial sum and it converges, then your series will converge, and the actual sum of the series will be what that limit of the nth partial sum equals. The other test for convergence that we have is the geometric series. If you recognize that your series is a geometric series where that common ratio r is a fraction between 0 and 1, and it can be positive or negative, then you know that your series will converge, and you can actually compute the sum to be a over 1 minus r. So these are two really powerful formulas because not only do they tell me that I converge, but they actually give me a way of figuring out what the sum actually is, which is pretty rare. The other things we know are two tests for divergence. The nth term test, if you take the limit not of your nth partial sum but of your nth term, so take the limit of those a sub n's, if that is not a 0, then you know automatically your series diverges. Also, you can use that geometric series as well. If you recognize that you have a geometric series but your common ratio is not a fraction, if it's bigger than 1 or less than negative 1, then you know that your series will diverge. Notice here that for that nth term test, if your limit of your nth term is 0, you can't conclude convergence or divergence. You'd have to try some other test to figure out whether it converges or diverges. So now we're going to try a few miscellaneous examples. Take a look at 0.23 repeating. We want to change this to a fraction. So there's a couple ways to do this, but we're going to treat this as an infinite series problem. So the way we're going to do that is we're going to expand out 0.23 repeating, and we're going to think of it as 0.23, 0.2, or 0.23, 23, 23, 23, and so on. Now these two decimal places, that goes out to the hundredths place. So 0.23 without any decimals after it would equal to 23 100ths. Now if I want to add in these next two decimal places, those go out to the, let's see, tenths, hundredths, thousandths, 10,000ths spot. So this 3 is in the 10,000 spot. So 23 in that position would be 23 10,000ths. So really what we're doing is we're kind of like taking 0.23 and then we're going to add to it 0.0023 and then we're going to add to it 0.000023. So each time we're adding on the next set of 23s. So this 23 is 23 100ths. This 23 is 23 10,000ths. This 23 would be 23 1,000,000ths. And so on. And if we add them all together, then we slowly get all of these decimal places filled in. So we continue this pattern. So if you rewrite your decimal as this sum of fractions, then this can be thought of as a geometric series, where your first term is this 23 100ths, so that's my A. And what you want to notice is that to get to the next term from here to here or from here to here, all I'm doing is I'm multiplying by 2 more zeros on the bottom, So I'm multiplying by a 1 over 100th, this whole fraction by 1 over 100th to get 2 more zeros in that denominator. So my r is 1 over 100. And the fact that that is a fraction less than 1 means this converges. And if it converges, that means it has a sum. And since it's geometric, our sum formula for a geometric series is a over 1 minus r. Our a is 23/100ths, and our r is 1/100th. So this is going to be 23/100ths over 1 minus 1/100th is 99/100ths. So these 100ths are going to cancel when I multiply by the reciprocal, and we get 23/99ths. So 0.23 repeating is the fraction 23/99ths. Okay, so you could take any repeating decimal and do this same process on it to figure out what it is in fraction form. The next example is an important one. It's called a telescoping series. We want to find the sum of 2 over 4n squared minus 1, the sum from 1 to infinity. Now normally, remember that in order to actually find a sum, we only have two formulas for that. Either it's a geometric series, and we use the formula a over 1 minus r, or we have some kind of formula for the nth partial sum, and we take the limit of that, and that is what our sum turns out to be. Well, this does not look geometric because we don't have some kind of fraction being raised to a power. We actually have a rational function here. So if we're going to have any success with actually finding the actual sum here, we're going to need to find some sort of formula for this s sub n. So let's see if we can work on that. Notice that 2 over 4n squared minus 1, that denominator actually factors. It's a difference of squares, so it's 2n minus 1 times 2n plus 1. And that means we can do a little bit of partial fractions on this. This can be broken down into an a over 2n minus 1 plus a b over a 2n plus 1. And if we get a common denominator on that right-hand side, then we can equate these two sides of the equation and figure out what our a and our b coefficients need to be. So my common denominator is going to give me these terms on the top in the numerator. So 2 has to equal a times 2n plus 1 plus b times 2n minus 1. Now if I let n equal to negative 1/2, which is going to make this 0, then 2 times negative 1/2 is negative 1. Negative 1 minus 1 is negative 2, and we'll get 2 equals negative 2b, so b must be negative 1. If I let n be positive 1/2, that's going to make this factor go to 0. 2 times 1/2 is 1, 1 plus 1 is 2, so we'll get 2 equals 2a, so a is positive 1. So that means this is the same as 1 over 2n minus 1 minus 1 over 2n plus 1. So instead of finding the sum of this series, let's find the sum instead of our partial fractions. And I'll show you why this is handy to do. Let's write out what this sum is actually going to look like. Let's write out some of the partial sums. So let's write out our s sub n. Our nth partial sum would be the first term when n is 1. So when n is 1, this is going to be 2 times 1, which is 2. 2 minus 1 is 1, so this will be 1. And when n is 1 in this fraction, we'll get 2 plus 1, which is a third. So that's what we get when n is 1. Then we're going to add to that what we get when n is 2. So that'll give me 4 minus 1, which is a third, minus 2 times 2 is 4. 4 plus 1 is 5, so we'll get a fifth. Then I'm going to add in when n is 3. So that'll give me 6 minus 1, which is a fifth, minus a seventh. And if I keep on going, for the nth term, when I use n equal to n, this will just be that 1 over 2n minus 1 minus 1 over 2n plus 1. So this is what the nth partial sum looks like. Now the reason this works out nicely, and this is why it's called a telescoping series, is because what you get with, especially with these partial fractions, is that these terms in the middle cancel. And so your nth partial sum is really just that very first term, the 1, and this very last term over here. So we were able to come up with a formula for our nth partial sum, which means we should be able to take the limit of it to get our sum of our series. So what's the limit of 1 minus 1 over 2n plus 1? Well, as n gets big, this denominator gets big, so this fraction goes to 0. So we just get 1 minus 0, which is 1. So the sum is the limit of these partial sums, so the sum of that whole series must be a 1. So be on the lookout for these telescoping series. These are going to occur when you have to find a sum of a series that looks like that denominator will factor and can be broken down into partial fractions. So when you have those partial fractions, that's typically going to cause you to get all of these middle terms to cancel, and then you'll be able to figure out what the sum is based on what's left. The next example, we want to find the first term in this series, 1 over 2 to the n, which is less than 0.0001. Does this series converge, and if so, what is the sum? So I'm actually going to answer the last two questions first, because this should be fairly obvious by now, looking at this series from 1 to infinity of 1 over 2 to the n. That's going to be 1/2 plus 1/4 plus 1/8 plus 1/16, and so on. That's geometric. And it's geometric because each time we're multiplying the next, to get the next term, we're multiplying by 1/2, this 1 over 2 right here. And the fact that that r, 1/2, is less than 1 means that this will converge. So we know it converges, and therefore we know its sum. Because for a geometric series that converges, the sum is a over 1 minus r. Our a, this first term, is 1/2, and our r is also 1/2. So we get 1/2, 1 minus a half is a half, and a half divided by a half is 1. So it converges with a sum equal to 1. So that is based on what we've talked about. The first part of this problem is a little different. We haven't done one like this, and this one is asking us to find the first term in the series, which is going to be less than 0.0001. So that's basically saying, when does one of these fractions eventually get less than 0.0001? Now you could certainly continue out and punch in your calculator until you find the one that works, or you can just write out what a generic term would look like, and that's this formula right here, 1 over 2 to the n, and let's find out when that generic formula is going to hit 0.001. When is it going to be less than that? And I have one too many zeros there, so let me fix that. So how do I solve this? Well, we are basically just going to multiply both sides by 2 to the n, and then I'm going to divide by that decimal. And you can do as much work here as you like. You can go on your calculator at any point here and just look at some tables. If you wanted to physically solve this for n, you could take an ln of both sides. I'm just doing a lot of algebra here, and none of this is really necessary. I'll show you in a moment how you can do it on your calculator. If I take an ln of both sides, then I can bring this n down and then divide both sides by ln of 2. So the n that's going to work is going to be ln of 1 over 0.001 over the ln of 2, and that's going to be the very first n. That as soon as we hit an n greater than that, then that term, that fraction up here, will be less than 0.0001. And if you punch that into your calculator, this is about 13.29. So if I choose an n like 14, I know for sure that this term will be less than 0.0001. So we need our n to be greater than approximately 13.29. Now the other option is just to pull up your calculator, and we're basically going to type in 1 over 2 to the n into our y equals, and then look in our table until we see when it first becomes less than 0.0001. So if you go to your calculator and just type in 1 divided by 2 raised to the x, and then go to your table set, let's start it at 1 and go up by 1s, and then go to table, and then you're just scrolling through in these y values over here until you see the first one that's smaller than 0.0001. And you do get into some scientific notation here, and when I get to that 13th number, 0.00012 is going to be this decimal right here. So when I get to the 14th number, this is going to be 0.000061. So that's definitely smaller than 0.0001. So the 14th value for n will give me the first term that's going to be smaller than what I was looking for. Okay? So that's one of your options. Now we're going to do the same thing on this next example. We want the sum from n equals 1 to infinity of 0.01 to the n. We want to find the first term in that series, which is less than 0.0001. Does the series converge? And if so, what is the sum? So just by looking at this, I know that this is going to be a geometric series because I'm multiplying each term by 0.01 each time. So the first term is 0.01, and then the second term is 0.01 squared, and then the third term is 0.01 cubed, and so forth. So this is geometric. My ratio r is equal to that 0.01, which is obviously less than 1, so this will converge. And the sum is going to be a over 1 minus r. The a is this very first term, 0.01, and the r is 0.01. So we'll get 0.01 divided by 1 minus 0.01, which is 0.99, and 0.01 divided by 0.99 is 0.01 repeating. So it does converge with a sum equal to 0.01 repeating. Now let's find our first term in the series that's less than 0.0001. So all you have to do is take that generic a sub n, which is our 0.01 to the n, and we want to find when is that going to be less than 0.001. You can get fancy, you can take an ln of both sides, bring your power down, divide by your coefficient and solve for n, or you can just pull up your calculator, type it into your y equals, and hit table, and I'm going to scroll up here, and we're looking for when this is going to be less than 0.001, 3 zeros, and right away when n is 2, 1 times 10 to the negative 4th is 0.0001. So as long as we pick an n bigger than 2, these are all going to be smaller than that required decimal that we were looking for. So our solution here is this is true when n is bigger than 2. So this converges really quickly. We got to that small decimal value very fast. Up here, 13, if I pick n to be 14 or higher, we're going to be smaller than that 0.0001. So this converged fairly quickly, but this one is obviously much, much faster, and that's because your r is much smaller. All right, find the first term in the series 1 over n, which is less than 0.0001. Does the series converge? If so, what is the sum? Now this one's a tougher one because 1 over n is not a geometric series. It's not a fraction or a number being raised to a power. It's just 1 over n. So what we want to do here is be a little bit more creative. We can't use our geometric series sum formula. So what we're going to want to do here if we want to try to find out if the series converges, if it's not geometric, then our only other option is to think about those partial sums, because that's the only other way we can figure out what the sum is if we know we don't have a geometric series. So let's write out what some of these partial sums are going to be. And to help us out, let's write out what our sum is going to look like. When n is 1, this is just 1. When n is 2, this is a half. When n is 3, we get a third, plus a fourth, plus a fifth, and so on. So the first partial sum would just be this very first term, 1. The second partial sum is going to be 1 plus a half, which is 3 halves, or 1.5. The third partial sum will be 1 plus a half plus a third, and if you get a common denominator there, this is 11/6, which is 1.83 repeating. The fourth partial sum is 1 plus a half plus a third plus a fourth, which is 25/12, and that's 2.083 repeating. The fifth partial sum, 1 plus a half plus a third plus a fourth plus a fifth, is 137/60, which is 2.283 repeating. And just to give you an idea here, this is kind of tedious, but you can use some technology to help you figure out the 1000th partial sum, which is about 7.49. The 2000th partial sum is about 8.18. The 3000th partial sum is 8.59, and the 248,042 partial sum is 13.00067. So looking at these numbers here, they're getting bigger, but they're getting bigger very slowly. I mean, all the way up to the 248,000th term, we're still only at a sum of 13. So this is very, very slow, and it's quite difficult to come up with an actual formula for S sub n. That's tricky to do in this kind of a problem. It's hard to come up with that. And based on just these numbers and these examples, it doesn't look like it converges. So we're going to see in future lectures a way to prove that this does not converge. But we can kind of, based on instinct, maybe see that this isn't going to converge because it's so slowly growing. Okay, it's very slowly growing. So let's take a look at what term in our sequence is going to be less than 0.0001. So our generic term is 1 over n, and we want to know when is that going to be less than 0.0001. So if I cross multiply here by n and then divide by 0.001, 1 divided by 0.0001 is 10,000. So it's going to take me up to more than 10,000 terms until one of these fractions is smaller than this decimal right here. And that's just further proof that this is very slowly adding to our sum. So each of these fractions just adds a little tiny bit more to our sum, but it's not sufficient to show that it converges or not. So we're going to just base our conclusion that it diverges based on these examples here, and in a future video lecture we'll get a more concrete way of proving that it truly does diverge. Our last example here. The radius of a large sphere is 1. To the large sphere, 9 spheres of radius 1/3 are attached. To each of these, 9 spheres of radius 1/9 are attached. This process continues infinitely. So you can even think of this as a fractal. Show that the surface area is infinite. Okay, so we want surface area, and these are spheres. So let's first recall that surface area formula for a sphere is 4 pi r squared. So let's talk about our very first sphere, our largest one. It's a sphere of radius 1. So what would its surface area be? Well, it would be 4 pi times that 1 squared. And then what are we doing to that sphere? We're adding to it 9 spheres that each have a radius of 1/3. So each of those smaller spheres are going to have a surface area of 4 pi times 1/3 squared. And then what am I doing to those? Well, I'm adding to those 9 more, and it's 9 times the 9 that I already had right here for spheres that have a radius of 1/9. So I'm going to have a surface area of 4 pi times 1/9 squared for each of those. So for all 9 of those, 9 more are added. And this process continues. So let's figure out what these are. Let's simplify it a little bit. 4 pi times 1 squared is just 4 pi. 1/3 squared is 1/9, which is going to cancel out this 9, so we're going to be left with 4 pi. 1/9 squared is 181, which is going to cancel out both of those 9s, so this will be 4 pi as well. So as you can see from the trend here, that I'm going to get an infinite number of surface areas that are each 4 pi. So this is going to be like 4 pi times an infinite number. And so this is infinite, so our surface area is infinite. And this is the idea behind fractals, where you have this repeated process, adding the same amount each time, and you get this sort of fractal pattern. So it's kind of cool. All right, that concludes our video lecture on infinite series. Good luck.